Today we're going to talk about Newton's second law. We're going to look at how to the basics of it, the units that go with it, and how we can reason along with it. So Newton's second law, it's really just a way of thinking of Newton's first law in a quantitative way. Remember we said that as an object in motion remains in motion unless there's an unbalanced external force. So if there is an unbalanced external force, or a net force as we're going to call it, that force will change the motion. It will cause acceleration. We talked about all those things before, but now we're going to make it so it's quantitative so we can solve for exactly how much it changes. The relationship that ends up being derived is the net force, the total force on an object, equals its mass times its acceleration. So the more force you put on it, the more acceleration you'll get, assuming the mass remains constant. And they'll be proportional. If I have 10 times more force, I'll have 10 times more acceleration. We shorten it usually to F equals ma. It's, that's the standard form. The actual Newton's derivation was actually acceleration equals force over mass, which is cool too, but this is an easier way for solving. So there's the equation, F equals ma. The F obviously is the net force in the units, or newtons. The m is the mass measured in kilograms. So if you're given a number in grams, you have to convert it to kilograms in order to solve. And the acceleration is in meters per second squared. Now you'll notice that there's newtons and there's kilograms and there's meters per second squared. So how do those all work together? They work like this, that 1 Newton is 1 kilogram times 1 meter per second squared. So if you push with 1 Newton, it's enough to make 1 kilogram accelerate at a rate of 1 meter per second squared. That's how they convert together. So let's look at a basic problem. A crate has a mass of 10 kilograms and an acceleration of 0.91 meters per second squared. What is the net force on the object? So all we do is we put down the equation, F equals ma. We know that the mass is 10 kilograms from above and that the acceleration is 9.1 meters per second squared. We take those, we multiply them, and we get that the force is 91 kilograms meters per second squared, which is the same thing as 91 newtons. So again, you can see the math for that is relatively straightforward. We'll try another basic-ish problem on the next slide. For this one, when a dog runs, a net force of 15 newtons acts on it. If the dog's mass is 25 kilograms, what is its acceleration while this force is applied? Well, we're going to start with the equation again, F equals ma. But this time they tell us the net force, which we put in is 15 newtons. We put in the mass as 25 kilograms times A. This time we're going to have to divide, not multiply. So we're going to take the 15 newtons and divide it by 25 kilograms. We get 0.6 newtons per kilogram, which, as long as we stuck to the same units we had before, will be meters per second squared. Now we're going to reason a little bit with Newton's second law. And there are lots of ways to do this. You don't have to use the technique that I'm going to show you, but if you have a hard time with sort of visualizing that kind of abstract, like this increases and this decreases, this is a method that can help. So you're not going to solve for an exact answer. You're going to solve for a change in the original answer, like how much different is it than the original answer. So the way I do it, I use brackets with the change percentages in them. So like, for example, like if there's no change, you just put a 1, because 100% of anything is just itself. So I just put a 1 in the brackets. If I double it, I put 2 in the brackets. Or if I cut it in half, I put 1/2 in the brackets. Or you can put 0.5 if you remember that that's the number that goes with that percentage. But those are the ways we're going to convert. And then I'll show you how we're going to use it with a couple of examples. The first one, if the acceleration of a boat doubles while its throttle is increased, how does the boat's acceleration change? And we're going to assume that the mass of the boat stays constant. Well, again, I'm going back to the equation, F equals ma. The mass stays the same, so I put a 1 in the brackets. The acceleration doubles. I put a 2 in the brackets because it's twice the original amount. And I take those two bracketed things, I multiply them. 1 times 2. Well, that's not hard math. It's just 2. But it's in the brackets, so it doesn't mean that there are 2 newtons. all it means is that they're 2 times the original force. So the net force must have doubled when the throttle was increased in the problem. Here's another example. A circus performer launched a clown out of a cannon. If the net force from the cannon is only 1/3 of the force from last night's performance, what does it mean about the clown's acceleration during this performance? And again, the clown's mass is going to be constant between the two performances. We're making some assumptions about the clown. I'm going to start with the Newton's second law, F equals ma. Again, the mass stays the same, so I'm going to put a 1 in the brackets, just like before. But this time the net force is different. It's 1/3 of the original amount. So I did 1/3. I put them in the equation, the bracket for 1/3 for the net force and 1 for the mass. Again, I end up dividing those. I take 1/3 divided by 1. I just get 1/3. So it means I have 1/3 of the acceleration. Now, I recognize that these two examples are pretty easy ones to do, and maybe you could have done them even without using this technique, but I'll show you why it comes in handy in a more complex example. So we got a wagon full of stones, and it's pulled with a specific net force. The force is increased to twice the original force, but stones fall out as it's pulled, but the new acceleration becomes 5 times the original acceleration. So how does the mass change when it's pulled? Well, you can see now both things change, so that gets to be kind of a hard thing to figure out. So let's see what we can do with it. So again, I'm going to start with force equals mass times acceleration. Net force equals mass times acceleration. The acceleration is 5 times greater, so I put 5 in brackets. The net force is twice as much, so that's a 2 in brackets. And then I'm going to put those brackets into my Newton's second law equation. So 2 in brackets equals m in brackets times 5 in brackets. So to get the mass by itself, I'm going to divide both sides by 5. So the mass is going to be 2/5 or 2/5. So the mass of the wagon with the stones after pulling that hard will be 2/5 of the original mass. So that gives you a pretty good idea how to solve these. So that's it.